A cylinder rolls without slipping over a horizontal plane. The radius of the cylinder is equal to r. Find the curvature radii of trajectories traced out by the points A and B. So here we have this cylinder, and this is the center of the cylinder C, and let it is accelerating with acceleration W. It is given. Clear? So what we have to find out? We have to find out the trajectory curvature of this point A and of this point B. Now I am going to solve this question in two different formats. One format is definition based, and the other method is based on the inferred results from the concept of rolling without slipping and what we have learned in question 1.3 earlier. So first of all, I am solving this question using the procedure of definition. As per the definition, the radius of curvature of a given point, that it is denoted by Rp. So this radius of curvature of a given point in such a situation is equal to the cube of the magnitude of the velocity of that point divided by the modulus of, or the magnitude of, the cross product of the acceleration of that point with the velocity of that point. So in order to get this radius of curvature of a particular point, here these points are A and B, we need velocity of point A and B and the acceleration of point A and B. Clear? Now suppose this is point A and the acceleration of center of mass is W. So let this is x-axis and let this is y-axis. Clear? So the acceleration is in this direction, that is x-axis. So the tangential acceleration is wi cap, and the acceleration of center of mass at this point A is also this wi cap. Now acceleration along the radius towards the center is the centripetal acceleration, and that acceleration is r omega square. Omega is the angular velocity of the circular symmetric object at that instant, and it is minus j cap. Clear? So this is the acceleration of center of mass, this is the tangential acceleration, and this is the centripetal acceleration. Clear? So acceleration of point A is equal to twice wi cap, as both are in the same direction, plus the radial acceleration, so this is r omega square minus j cap. So this is the acceleration of point A. Now velocity of point A, the tangential velocity is in this direction and the velocity of center of mass is in the same direction. So this is point A, and the net velocity of point A is the vector sum of the tangential velocity plus the velocity of center of mass. So as it is under pure rolling, the velocity of center of mass is r omega I cap, and tangential velocity of point A is r omega I cap, and if we add them, so we will get 2r omega I cap. Clear? Now if we substitute this VA and this A, acceleration of point A, in this result for the radius of curvature, so A cross VA, we will get, so this is AA, so I cross I will be 0 and I cross J will be K and minus K, and as we are taking the modulus, so we will get 2r square omega cube. Clear? And the magnitude of this velocity of point A is magnitude is equal to 2r omega. So if we substitute both these results here, so we will get the radius of curvature of point A equal to 2r omega cube divided by this 2r square omega cube, and if we solve it we will get 4r. So this is the radius of curvature of point A. Now we can solve this problem in another format, as I have told you earlier from the inferred result case. Let this is point A, clear, and the velocity of point A is equal to twice the velocity of the center of mass from the concept of rolling, clear, and the centripetal acceleration is acting toward the center. So this is point A, and the centripetal acceleration magnitude is equal to r omega square. Now from the concept of the centripetal acceleration, if A is the centripetal or radial acceleration, so this is equal to v square by the radius of curvature, clear. So from here we can write RA is equal to v of that point, it is 2 times VC's r omega whole square divided by the magnitude of this acceleration, that is r omega square. So from here we can have the same result, that is equal to 4r. So you can choose any method, either this definition approach, this is a mathematical derivation and it is not in our general syllabus of physics up to +2 level, and if you want to derive this result or want to have some mathematical confidence, you can search online. I am giving a link from where you can have the confidence about this result, that is math online wiki.com, and you can put curvature of a point, From here you can see the derivation of this result if you think you want to solve this question using this method, clear. Otherwise you can use this procedure also, clear. Now what about point B? So for point B I am using this short method. So the velocity of point B in this direction is say v, and the velocity in the tangent or velocity along the tangent is also v, because it is under rolling. So the resultant velocity of point B is under root 2v, clear, and v is r omega, clear. And this is the direction of the centripetal acceleration that is acting towards the center. Centripetal acceleration you can denote it by AR, clear. Now what we want to find the radius of curvature of point B. So for this we need this v square by acceleration of point B. Now the condition here is this v and the acceleration corresponding to this point B must be perpendicular to each other in order to substitute in this formula. Now what is the acceleration in this direction? So this is perpendicular to this net velocity. As this is v, so this is 45 degree, this is also 45 degree, and this is also 45 degree, clear. So this is 45 degree. So this component of acceleration in this direction is AC cos of 45 degree. So the radius of curvature of point B is equal to the velocity of this point B, that is under root 2v whole square, divided by the acceleration. Acceleration is AC cos 45 degrees 1 by under root 2. Clear? So we have this 2 under root 2 v square is r square omega square divided by the acceleration magnitude. This is radial acceleration, so this is r omega square. So from here we get the value of radius of curvature of point B as 2 under root 2 r. Clear? Now if you want to solve the question using the definition approach, now this is point B, and let this point B is origin. Now the velocity of point B is the vector sum of the velocity of the center of mass plus the tangential velocity. Clear? So the velocity of point B is the vector sum of these two velocities. So the velocity of point B is equal to the velocity of point C, means center of mass. So this is VC I cap minus VT J cap. Clear? And as the magnitude of VC and VT same, so we can write R omega I cap minus R omega J cap. Clear? And the acceleration of point B is the vector sum of all the three accelerations. Acceleration of center of mass, that is AC I cap, minus the radial acceleration. Now that radial acceleration is acting toward the center in the negative x direction, so this is the direction of the radial acceleration, and the direction of the tangential the direction of the acceleration of the center of mass is along positive x, and the direction of the tangential acceleration is along negative y direction. Clear? And if we substitute the values, AC, the acceleration of center of mass is W as shown in the figure. This is W. Clear? And the radial acceleration is R omega square I cap minus tangential acceleration will also be W, as we have solved in earlier question 1.53. This is J cap. So from here we have W minus R omega square I cap minus W J cap. Now in order to get the radius of curvature of point B, we need this AB cross VB magnitude and the cube of the magnitude of VB. Clear? So the magnitude of VB is equal to under root 2 R omega, and AB cross VB, AB cross VB. So this AB cross VB, if you solve it, you will get R square omega cube. Clear? This you can solve. So if we substitute the value here, we have under root 2 R omega whole cube divided by R square omega cube, and if we solve it, we will get 2 under root 2 R. Clear? So this is our desired result. So you can solve this question in any form you like.